Hi everyone. Thanks for being here, and I'm excited to take a part of this tutorial. Uh, Let me give you a quick overview of our experience and the project we made at Poznan University of Technology. So this project, it was a collaboration with Samsung Electronics in Poland, and we make cargo platform. It's kind of a challenge because we had just 3 months to deliver a working prototype. So, and we start with our old vehicle. The platform was based on Melex vehicle. It's a well-known Polish vehicle, and we integrate everything with Autoware. I was a student and I was a part of a team, and my responsibility was to create and design low-level driver for the vehicle, and also I take a part in localization and control planning modules, and make sure that the entire platform work correct together. We started at our campus, and step by step we migrate components with our cargo platform. So the biggest challenge was making sure that the all components working on real and dynamic and changing condition environment. We had to carefully set everything and test it and make sure that's worked. One of the most important part was precise parking, and was needed so vehicle could be picked up by the indoor mobile platforms like AGV. We handle it with the low-mounted 2D safety scanners. When the localization by GNSS was limited, we use it as a source of position. By the end, we're able to navigate through entire factory and between predefined location. So these are our Melex platforms. Both were built on same suspension, and mechanically they were quite robust. However, they weren't originally created for such a task because it doesn't have steer-by-wire from scratch. We made it from the scratch. Like most prototypes, we encountered many unexpected issues like redesigns and technical workarounds through the process. And the cargo platform was a big step further because everything we learned before from technical perspective, it was much more refined. But there was a trade-off because the system became quite complex, and the entry barrier was high. That made it harder for new students or developers to jump in to project and start experimenting and As the result, fast prototyping became more difficult. So that experience gave us an important lesson. Building fuel scale vehicles, it has benefits, but also complexity, cost, and maintenance overhead. For early stage development and student research, we realized we need something simpler, faster to iterate, and easier to work with. So it's just F1 test platform, which is lightweight, safe to test, and quick to build and modify, so we can really push it to the limits. And don't worry about breaking expensive hardware. So building our experience with F1 10 platform and challenge faced in F1 10 competition, we explore more advanced control algorithms, and we are proud that our work was accepted to IROS last week, where we present a racing policy, entirely trained in simulation, and transfer it to real vehicle without any fine tuning.
In this video, we would like to present a paper titled On Learning Racing Policies with Reinforcement Learning. Autonomous racing serves as a crucial test for pushing vehicle control to its limits, providing insights applicable to real-world self-driving cars. This work aims to identify the key factors necessary for successfully training racing policies in simulation and deploying them in real-world racing scenarios. For our experiments, we utilized an F10th racing car, modeling its dynamics using data from a motion capture system. This allowed us to create a highly accurate simulation environment for training our reinforcement learning policies. A fundamental challenge in RL is transferring policies trained in simulation to real world, which we address by systematically studying methods that enhance sim-to-real performance. We conducted a comprehensive evaluation of how domain randomization, policy architecture, and actuator modeling influence the real-world performance of trained policies, highlighting the importance of these factors in developing fast and adaptable RL policies for real world. Our results demonstrate that our RL-based policy outperformed the state-of-the-art model predictive control algorithm. More significantly, it also surpassed expert human drivers in both the fastest lap time and the average lap time over 20 laps, marking, to our knowledge, the first instance of an RL policy surpassing human experts in real-world RC racing. Here you can see a direct comparison between the lap of an expert human driver and the lap of our RL policy. Our policy effectively operates at the vehicle's limits while demonstrating remarkable robustness. It successfully recovers from substantial slips and maintains control in situations where traditional controllers or human drivers may struggle. Thank you for your attention.
If you want to explore for full article, please scan the QR code. This is the project of my colleagues, which I'm really proud of.
In this video, we would like to present.
We use OptiTrack in our lab. Yes, it was. When we start on autonomous vehicles, we knew one thing for sure: building everything from scratch wasn't an option for us. And fully autonomy is just too complex and time consuming, especially for a small team. That's why we choose Autoware. And it's open source, modular, and already includes many of core components you need in autonomous system. Instead of spending time reinventing those blocks, we could focus on our contribution, like state estimation, control, or extended Kalmar filter tuning instead implementing it again. So it's another key benefit is how it can be customized. Autoware is designed to swap out modules and try different planner, object detector, and bring it your own control logic. It's flexible and and one of the most important thing for us is Autoware is student friendly because student works on ROS2 and same tool used in education, and they can study real system architecture, modify code, and run it in simulation or on the real vehicle. So the hardware and actually they can understand how a full stack vehicle works. So Autoware is for us not just a technical solution, but also education platform, which help us to train the next generation of robotics. So let me introduce you the Pixel platform. It's specially designed for autonomous driving research and for education and also for industry. The base platform weighs 500 kilograms and make it compact, but still robust enough for real world experiments. It can reach speed up to 40 kilometers per hour and has 4-wheel drive, making it easy to handle even on mixed terrain. And one of key features is fully exposed CAN interface. Pixloop has 3 steering modes, including front wheel, all wheel, and crab steering. It's very flexible. It's very helpful, especially in tight spaces or teleoperation. Honestly, the crab steering mode is one of the first thing people want to try. It looks weird, but it's really practical. And PixKit mentioned before. It includes everything you need to get started, and this is the platform and sensor suite. It's basically plug and play solution. PixKit version 3. It's the latest evolution of the PixMoving development platform, and brings it closer to full scale vehicle. The most obvious change is the addition of the body and CPU. It's the platform, but it's something actually you can sit, ride, and interact with more like a car. our previous Melex had reached the end of its useful life, so we decided to change it. While the base Pixloop is already a solid solution, we decided to get further and build our custom sensor kit based on everything we learned from previous project. We also design and build protective enclosure. It's fully waterproof for onboard computer, and there is a lot of space for additional battery or inverter, so we can, for example, power the laptop on test field or test the autonomy in rain. So we focus on two things, precise localization and reach perception. We installed two GNSS antennas with a long base because 1.8 meters and give us much better heading estimation. For perception, we went to full 360 degree LiDAR coverage and nearly complete visual coverage from 4 wide angle cameras. So it's our platform ready to start research and development. So clue question, what do you need for integration? There are three essential components: vehicle model, sensor model, and vehicle driver. So vehicle model is just a description about vehicle and its size, physical geometry, its size, shapes, wheelbase. It's critical for localization, path planning, and control, and also it's divided to packages like vehicle description with these parameters, and also mesh model, and the vehicle launch, which needs to bring that model into ROS environment. So when it comes to vehicle model, we didn't start from scratch. PixMoving actually provide vehicle description and launch package for the platform. So it's great starting point with the hardware. However, since we using Pixloop for research and development, we made a few important updates. First, we update the package for the latest Autoware release, and second, we replace the 3D mesh model to optimize model, which made tools like Foxglove or RVs much more responsive, especially during live session. It's more change, but it make big difference in day-to-day workflow. The sensor model, it's basically the exact mount position of each sensor, how they connect to the robot, and which drivers and launch files are needed to start the sensors like LiDAR, cameras, GNSS. It's simply to describe their position using YAM file and tie everything together. It's not about just visualization, but it's critical for sensor fusion and accurate localization. So it's truly backbone of perception. For calibration, we use tools like Calib to give us the internal parameters of position of cameras, and relative to each other cameras, it's very useful for stereo or multi-camera system. For align LiDAR to other sensor, we use tier 4 calibration tools. It's built to work with Autoware. And help align LiDAR to base, camera to LiDAR, and LiDAR to LiDAR. And the calibration results are saved as static function for the rest of the system. So once all the sensors are calibrated, then the system can start working as a whole. You can see a live perception visualization during teleoperation. It's a great way to debug and validate perception performance before start autonomy. Vehicle driver. This graph shows official the PIX interface provided by PIX Moving. It's designed to connect Autoware. We have flag, I think. Okay.
Not just the network.
Okay. Now you see what I see. This graph shows us architecture of PIX interface provided by PIX Moving. It's designed to connect Autoware with the drive-by-wire vehicle using the CAN bus. The interface has three main function. It's translate low-level CAN to ROS2 messages, takes feedback from the vehicle, like speed, gear, and steering, and translate it back to Autoware messages, and converts raw vehicle commands into control messages to PIX platform. It's ROS2 native and modular, so it's easy to integrate with Autoware control. In our experience, it worked well and easy to adapt, but I would like to draw your attention to component raw vehicle command converter, which sits inside the Autoware stack, and PIX Moving use it. So this node is responsible for converting high-level trajectory output from Autoware and control modules and into a format that interface can understand. Because it's also time-consuming to calibrate this package, we don't use it because raw vehicle raw vehicle command converter is an important part, but not always best fit for especially for electric vehicle. This package was designed for fuel-powered vehicle in mind, where engine behavior is non-linear. So it outputs like things like throttle percentage and brake pressure based on complex mapping. So we can see on plot here, it depends on things like RPM and torque curves. But with electric vehicles, the response is much more predictable. We can usually just command velocity direct, and low-level PID control should control it. So also the interface supports target speed command. So unlike fuel-based platforms that required throttle and brake percentage, the PIX vehicle give us direct control over the speed, and that's why we don't need raw vehicle command converter at all. And as you can see this updated diagram, we removed that node entirely and changed interface in control converter node. It makes the control loop simpler and more responsive, which is important for us. So overall, this change better reflects what hardware we have and give us more deterministic control. Pixdriver is available on GitHub from PixMoving company, and includes everything you need to get started with CAN communication, control commands, translation, and integration with Autoware. But we forked it and make several key improvements. We added vehicle commands control, and rather than stay on torque control and give us better performance. And also we change, we add dynamic steering mode switching, which wasn't available by default, which is especially useful when we have free mode steering and experimenting with tight motion strategies. Once our improvements are fully validated, we will pull request so entire community can benefit from our feature. I want to introduce you tools like Autoware default at API, which serves as the backbone for managing Autoware API layers. It handles important system level logic. It's okay. This tool handles important system logic and like switching between modes and handling routes and managing fail behavior when something go wrong. And this is a simple example of usage. Is an example of how to use GuidePy in practice. The scripts give us clear human-read diagnostics about the current system state. So in case you can see that detecting common issues like no pause or no route or something is wrong with the car. So instead of digging through logs and checking dozen of topics manually, GuidePy gives us a quick overview of what's missing or blocking. And also okay. And also equal important packages which help us with system startup and debugging is diagnostic graph monitor, which is a visual tool that help us to inspect overall health. It displays diagnostics tree showing how different components are connected, and more important, where things are failed. This is especially useful for tracking node failure, topic rate issue, and if there are even emergency states or incorrect operation modes. So basically, you can trace what's blocking Autoware from switching to autonomous mode by following the autonomous path. We found this tool is very helpful during testing and integration new platform, especially when issues that aren't obvious from logs or command line. So that's all from my side. I hope this overview gave you a clear picture of our integration work with, and I would like to, if you would like to connect or follow our contribution, feel free to scan the QR code. And now I'm ready for your question.